Okay, so welcome back. So in the last session we have defined what is sheaf, what is pre-sheaf. Also we have discussed several examples of pre-sheaves, and we have seen that every pre-sheaf is a sheaf by definition, but may not be. It is not necessary for a sheaf to be a pre-sheaf. For example, we have considered the constant pre-sheaf. But there is a way to give a unique sheaf structure on a pre-sheaf, that is called something called sheafification, that we'll study. And I also gave you an exercise to work out with skyscraper sheaf. I hope you have done. Let me just give you a brief overview that skyscraper sheaf is basically defined on a particular point. Skyscraper at a particular point. So the morphisms rho uv, these are basically the zero map or the zero homomorphism, whatever, an identity. Okay, and based on these two things, you can say that it is a sheaf. It has a sheaf structure. In fact, based on this, it has a pre-sheaf structure, and you can get that it is a sheaf. It also has a sheaf structure. Now let us move in our next discussion. So remember that if we are given, let's say, topological space X and a pre-sheaf or sheaf, whatever, now we'll study what is sheaf, or let's say pre-sheaf, whatever. So pre-sheaf on the category of open sets of X, here to category of abelian group. So if this is a sheaf, then every open set U is taken to an abelian group. Now we will get some local setup related to sheaf. Means if we want to study a particular some properties of F, I will try to get such a local setup such that it is enough to study the property of sheaf or the property of abelian groups obtained via the sheaves. In that local setup, it is enough to discuss about the sheaf. So that is called something. So as I am taking consider local, so of course I will try to restrict my discussion at a particular point. So it is stock of a sheaf or pre-sheaf, whatever, at a point. So what is stock? So let us consider F is a sheaf on X, okay, and P belongs to capital U. Now we are considering a system, let's say F of U, such that P belongs to U, and rho UV such that U is superset of V. So you see that this is a direct system. So as it is a direct system, means if you want to just more simplification is enough, is fine, that if you take, let's say, U subset of V superset of W, and of course rho UW is nothing but rho UV composed with rho VW. Okay, and rho UU is identity map. So then, by the definition of sheaf and also the restriction maps, how it is defined, the system is a direct system. Now, as it is a direct system of what? So it is a direct system of abelian groups. Okay, so as it is a direct system of abelian groups, so you can say that it must have a direct limit. Right? So as it is a direct limit, let us consider that direct limit f of u, p belongs to u. So this is said to be stock of f at p. Okay, so now one should be mentioned. Okay, so first now see one thing, that each fu, these are abelian groups, so the direct limit is also an abelian group. We denote it as fp. So that means if you are given with a particular sheaf f, then for every point small p in capital X, you can achieve a abelian group f of p. Now you know how to deal with abelian groups. So this is the way to transform a particular operation, a particular sheaf, and how to obtain a particular abelian group from a given sheaf. This is the way. Now, why I have said that it is a local setup? Why I say it is a local setup? Remember that if you take any 2 points p comma q belongs to capital X topological space, then fp and f of q may not be same. For example, in a while we will say that we will study something called spec of A or spec A. This is called, it's an affine scheme. It's called spectrum of A. In this case, at every point P belongs to spec A. In fact, each P are prime ideals of A, where A is a ring, commutative ring plus unity. Each prime ideal, the Stalks looks like AP, A localized at P. Now, if you change, if you take any 2 prime ideals, then you can easily say that AP may not be same as AQ. If you change the prime ideals P and Q, then the localization of A at both the prime ideals may not be same. So that means that the Stalks may change with respect to the change of this point. So that's why you can see this local setup. Now, why it is enough to study a local properties of pre-sheaf. So remember that suppose we have a direct system. So let us consider that let's say ui, I belongs to capital A, where capital A is a directed set, and rho ij I equals j. This is my direct system. So how the direct system is defined? The direct system is defined via some system. So this direct limit of ui, this is basically defined by using equivalence relation, right? In fact, the equivalence relations are defined how they are defined. So I say that ui not ui, we'll take disjoint union of all ui's, and I will quotient it with the equivalence relation. So the equivalence relations are following that let take any 2 points I1 comma I2 belongs to capital I. Then let's say x1 belongs to ui1 and x2 belongs to ui2. Then I say that x1 and x2 related if and only if there exists I3 belongs to capital I, such that rho I1 I3 of x1 is same as rho I2 I3 of x2, and yes, I1 I3 related to I3 and I2 related to I3. So then rho u1 I1 I3 and rho I2 I3 equal to rho x2 I3. So that means you can say that the equivalence class of x1 is same as equivalence class of x2, and this is true if and only if this condition is satisfied. So from the same perspective, how the direct limit will be defined. So the direct limit will be defined as should be defined that I will take all disjoint union of f of u and restrict with a equivalence relation such that there exists u contained in w and v contained in w such that rho uw, let's say s1 belongs to f of u and s2 belongs to f of v. Rho uw of s1 is same as rho vw of s2, means the restriction maps are same. So s1 is restricted at w same as s2 restricted. Okay, I'm sorry. What happened? So now the elements of fp, I should mention it here that the elements of fp should looks like u comma s such that s belongs to f of u. Okay, so when we say that two elements u comma s is same as v comma t, so from this perspective there exists some w inside. So note that w is inside v as well as in v, so I can write w is inside u intersection v. This is enough condition, right? So that means that s restricted at w same as t restricted w, and this particular condition takes care of the equality of these two elements. Okay, so that's why if you have two elements like this, then it's enough to work out any one of them, maybe on s or in t. Okay, yeah. Now we have already said that fp is an abelian group. So as it is an abelian group, so what should be the group structure? So the group structure is the following, that if you take U comma S star V comma T, V comma T, this should looks like U intersection V comma S times U intersection V dot T times U intersection V. Remember that once I have S restricted T intersection V, this particular one is in F of U intersection V, and this also is in here. That now as it is a group, so there is group usual group operation in between these two elements. So this is how one can define the group structure on FP. Okay. Now suppose F is a sheaf on X. So as it is a sheaf on X, then let's say from U I have F of U, and from V I have F of V. Again, suppose we have another sheaf G, which is from sheaf on X. So from U I have G of U, and V I have G of V. Let us assume that from FU to F of V the map is rho UV, restriction maps, and from GU to G of V the restriction map is, let's say, eta UV. Now both, all the FU, FV, GU, GV, all are groups. So I may be concerned that whether there is any connection between these two things or not. So that's why there is something called morphism between F and G. So is the morphism between F and G. So let us consider that we have two sheaves F and G on a particular topological space X. Then the morphism between F and G are nothing but the collection of all the FUs, let's say all the morphisms, all the group homomorphism, let's say phi UV. These are the group homomorphisms. These are from let's say not phi U, let's say all the group homomorphisms from phi U, from FU to GU, where U is subset of X is open set. For every open set is a morphism, is a collection of all such group homomorphisms such that the following property is satisfied. That means, so from phi U to GU I have phi U, and FU to FV to GV I have phi V, and also from FU to FV I have rho UV restriction, and GU to GV I have restriction. Now the condition says that this particular diagram should commute. That means phi U let's say, no, not phi U, yeah, let's say eta UV composed with phi U is same as phi v composed with phi v composed with rho uv. I'm sorry. Phi v composed with rho uv. That means that first you can take an element from here. Let's say you are taking particularly smallest from here, and we are applying phi u on this and getting some, let's say, phi u of s. Then we are restricting this at v. So it is same to take an element from here. So this particular thing is same, that first we restrict s at v and obtain s restricted at v, then apply phi of v. That means it doesn't matter that whether the element, whether we are restricting first or applying the homomorphism or vice versa. So whatever step we do initially, both are same. Now suppose we have, let's say, phi from f to g. This is a morphism of sheaves. So as there is a morphism of sheaves, what can now let us take the stock fp and stock gp. So my question is, can we obtain a group homomorphism from, let's say, phi p, let's call it a phi p, from fp to gp? So the natural way to define this morphism is that phi p of u comma s is nothing but u comma phi u of s. Just note one thing, that these particular morphisms phi v or this doesn't impact the open sets of the topological space. It just only works on the sections, right? So that's why if you take phi u of s, this must belongs to, sorry, gu must belongs to gu, right? So this is how we can define the morphism, and one can easily check that phi p is homomorphism. Like just using, so hint, use the characters property of similarity to elements of a stock. Okay, it's enough. And of course the group operation that is associated with the FP. Now there is something, now when we say that phi is isomorphism, so before studying isomorphism, let us consider one thing, that suppose I have a topological space X and I have three sheaves F, G and H. From F to G there is phi, from G to H there is she, and we are defining the composition of F and phi and she as usual, that is she composed phi, and it is defined as she composed phi of u is nothing but she of u composed phi of u. So The question is she composed phi? This is morphism from F to H. Let's check it up. So let us consider that Fu, here I have Gu and here I have Hu. Also here I have F of V, here I have H of V, and here I have G of V. Okay. So from F of U to F of V there is rho uv, G of U to G of V there is xi uv, here it is eta uv, and F of U to G of U there is phi u, here is she u, here is phi v, here is she v. Okay. Now let us consider a small s is from particular element here. So once you apply, you get it here that she of u composed with phi of u of small s. Then you are restricting at it here, that is you are obtaining she of u composed phi of u of small s. Oh, it's not working. Okay, fine. Let's take it this entire diagram in the next page. So here it is phi of u of small s, and here I am getting it as now restricting this phi of u composed, I'm sorry, is she of u composed phi of u small s whole restricted at v. Right? Now what is element here? So it is phi of u of small s. Right? So I should get it here that it is same as, now if we just restrict, so sorry, what's happening? So this restriction map phi of u is restricted at v, and apply it here, phi of v is restricted at phi of v of phi of u so this one and this one are same. Why? Because she is a she is a morphism between these two shapes. Means, what does this actually mean? This actually means that phi u of she u of phi u of s, once everything is done, then restriction at v. Right? So these two are same as this. That now, as these two are same as this, Now if you restrict it here, so now S restricted V you are obtaining here, then apply phi of V, okay, then you apply she of V. And in fact, what the, I mean, this inner part, what does this inner part means? This one actually implies, this particular one implies phi of V of A restricted V. So that means this entire one is dissolving at phi of she of V, sorry, it should be she of V of phi of V restricted. And this is more obvious that if you apply phi of V here, you will get this one. So that means if you take S here, apply the entire operation here, then restriction is in same to first restrict it, then enter the entire operation. That means she composed phi, this is also morphism of sheaves from F to H. Now suppose if we have two particular morphism, let's say phi is a morphism from F to G and she is a morphism from G to F, then phi compose she if it is identity over G and she composed phi if is identity over F, then you say that phi inverse is equal to she, means phi is invertible and F and G are isomorphic to G. So this is how one can define that if we have any two sheaves on a particular topological space, if we can get a morphism which has both sided inverse, then we can say that F and E are isomorphic to each other. There is a small exercise for you, that F and G are isomorphic if and only if FP and GP, these are isomorphic as abelian groups. Means to define isomorphism between two sheaves is enough to work out, so that for every particular point small t, the stalks are isomorphic. So it's a small exercise for you. The next session will continue from this one. If I try, I want you to try this first. Next session we'll start our discussion from here. Okay, so for today that's all.